We've talked about fluorescence spectroscopy in the previous lectures. Now we're going to talk about a new technique called Raman Spectroscopy, and the point of this video is to introduce you to the basics of it and to tell you about how it's different from fluorescence. So Raman spectroscopy is concerned with the vibrational modes of a molecule. So let's draw a sort of standard simplified molecule with two atoms attached by a molecular bond, a spring here. And conceptually, Raman spectroscopy is about shining in an excitation photon with energy E in, which I'll draw in blue, and the molecule gains some energy and it starts to vibrate more actively than it did before. So the photon loses some energy and scatters off in some different direction, potentially, with an energy E out. And that is the basic phenomenon of Raman scattering. Photon at one color comes in, photon at a different color comes out. You can think of it as an inelastic, instantaneous scattering event, and the molecule either gains or loses a quantum of vibrational energy. We can relate that to the same energy level diagram that we had in fluorescence. Let me make some of that appear for you here. Here you've got that plot of potential energy of the molecule as a function of the internuclear separation. And you'll recall that this well over here, this around the equilibrium separation of the two nuclei, we can draw in some oscillator levels like that, vibrational sublevels. And you'll also recall that we had a second excited electronic state. We called this perhaps the S0 electronic level. And then we had another one up here, sort of a copy of the first one. We're not going to play with that much here, but I'll just remind you about the basic idea that there was some excited state up here. So in fluorescence, this fluorescence process was a photon taking the molecule from the S0 state up to the S1 state. So there was an actual absorption from here up to here. In Raman spectroscopy, we don't deal with these so-called real states where we actually absorb the photon. We think about this incident photon taking us up to a level where there isn't any absorption available. We have not reached the level here of the S1 state, and that we will call a virtual state. In the virtual state, you have to get out of it really fast. I'll talk about that in a second. And the way that the molecule gets out of that state is to immediately emit a different photon. It could decide to go right back to the incident state that it started from and come all the way back down to here. That would be elastic scattering. But sometimes it emits down to here. And you'll see that we've got now an energy difference between the incident and the final state. And that energy difference, I'll call it delta E of vibration. And if this vibration over here has a frequency capital omega, then this one quantum of vibrational energy would have energy h bar, Planck's constant divided by 2 pi, times capital omega. So that's the energy difference between the incident and the scattered photon. So what did we mean by calling this level with the black dashed line here a virtual state? Well, as I said, it's a photon, an incident photon energy that the system doesn't truly absorb. There's no state for it to be in when it gains that particular amount of photon energy. So if we start unpacking what a virtual state means, the first assertion is that it's not a real allowed state. And we can then look at this energy gap between the virtual state and sort of the nearest actual state that's there. And this diagram looks like it's about that much energy. And we can call that the energy of detuning. There's a delta E of detuning there. Detuning in the sense that if we gave the photon, starting from the bottom, this much energy, we would be in line with an actual state, and we'd be tuning into an absorption resonance. But we're detuned from that. And it just works out that the amount of time that this molecule is allowed to actually spend in this virtual state is limited on the scale of femtoseconds. I'm not going to defend that exactly here, but by analogy with fluorescence, this virtual state has sort of a femtosecond lifetime. That's very, very fast on the time scale of vibrations, very fast even on the time scale of sharing energy with the environment. And the reason why it has such a short lifetime is that the time it can spend in that space is limited by the uncertainty principle. It's not truly forbidden in quantum mechanics to access a non-real level, but you can only do it for an amount of time that doesn't violate the uncertainty principle. So if you would have a relationship like this, that the delta t times a delta E has to be on the scale of Planck's constant. And in this case, we put delta E in the denominator because we're saying that delta t goes as h bar over delta E of detuning. And you don't have to worry about this argument too greatly. I just want to let you know that the farther away you are from any real state, quantum mechanics says that the more and more forbidden you are to be in that state. And so this delta t captures that, and I'm just asserting to you that it's on a very, very fast time scale of femtoseconds. Now, there are two consequences to the molecule not spending really any time in this virtual state. One is that it leads to a much lower quantum yield. In other words, Raman scattering is weak compared to fluorescence. Fluorescence has the ability to have a photon absorbed, and then it can sort of hang out in this upper state. It can relax down to the lowest vibrational level of the excited electronic state, and then on its own time schedule, it can emit a fluorescent photon. So there's an intermediate step, which is a real state, which allows it to have a greater probability of going from the initial state to an intermediate state to the place where it can then fluoresce. The Raman effect essentially has to happen immediately, and I will assert to you that that makes it a much less probable event to occur. You can simply think of it as there's no real state there. That sort of makes sense that it's not very likely that it's going to do this. But there is a chance it can, but it's pretty weak. So fluorescence effects are almost always much larger than Raman effects unless you get very lucky with the problem that you happen to be tackling. So that's a bad thing. But a good thing is that it also leads to a much narrower spectral line shape. And what I mean by that is that a real molecule has not just one mode of vibration and not just, it has many, many atoms in it. And once you absorb a photon, you can actually start sharing that energy among other aspects of the molecule. There are all sorts of things that can happen. But when you access a virtual state, you have to get right out of it essentially right away. There's no time to share that with anything else in the molecule. You aren't changing its electronic structure. And so that keeps you within this one vibrational manifold here. And so there's a very precise amount of energy, delta E, that's lost by every one of the photons that you send in. Once you let it interact with the greater complexity of the molecule, you tend to get lots and lots of possible emitted final photons. But not here. So because we stay within this little part of the game here, the spectrum of the Raman scattering that we get is very distinctive. I'm only indicating one such transition here. If you send photons onto a molecule that has many different vibrational modes, each vibrational degree of freedom will produce perhaps its own Raman scattering peak, and that sequence of peaks is very distinctive of that molecule compared to fluorescence, which is much broader and less distinctive. So we often call Raman spectroscopy the fingerprint of emissive spectroscopy compared to fluorescence. So a good thing and a bad thing. Okay, let's go back to the change in energy here that we got from E in and E out and start learning the language here. So we have a delta E of the vibration, and we can think of that as the energy in minus the energy out. So we can write energy in and energy out in terms of two fundamental constants, Planck's constant and the speed of light in vacuum. If we write lambda in the denominator, we have the energy of the incident photon. And if we write the exact same thing with the outgoing photon, we get the energy of the outgoing photon. And of course, we can group HC on the outside, and what we'll get is two terms here. 1 over lambda in minus 1 over lambda out. This quantity in the brackets here has units of inverse length, and it has a particular name in spectroscopy. We call it delta nu tilde, and we call that the wave number shift. And we often quote that in units of inverse centimeters. It doesn't have to be centimeters, but that's the conventional unit because it's convenient. It turns out that all of the four significant figures, if you say a shift is about 1005 wave numbers, it's usually accurate to within about one wave number. So this is the language here. When you see a delta nu tilde, you're talking essentially about an energy, but strictly speaking in terms of the number you're being given not an energy, but an energy without the HC part. So you're just getting 1 over length values. If you multiply it by Planck's constant and the speed of light in vacuum, you then get the change of energy between the incident and exiting photon. Now, why is this useful, this concept of the wave number shift? Because that's what we report Raman spectra in, is wave number shifts. Let's go back to this little delta E between two levels. Let me just draw two levels down here. And again, they have some energy difference delta E. And one thing that's interesting about Raman spectroscopy compared to fluorescence is that, let's suppose I come in with a laser that I might have tried to excite fluorescence with. So I start off in the ground state down here, and I excite the molecule up, and then it emits an outgoing photon, just like we have here. It scatters that a photon off. You can either think of it, by the way, as a new photon or as the scattered incident photon, but with less energy on an inelastic collision. But this is a situation that looks a lot like fluorescence. You have an energetic photon coming in, you have a less energetic photon that comes to your detector. But one thing that's different, I'll call this scenario A, is that if we had a tunable laser or some just different laser for whatever reason, we could have another scenario where we excite with a slightly different amount of energy. And if we undergo this same Raman scattering process that you see in the cartoon here, but we change E in, we're going to change E out. We have to, because no energy is lost anywhere else in the system between the initial and the final states associated with the Raman process. That's different from fluorescence, where if you recall, the photon gets absorbed, the molecule enters a state that's above its vibrational bottom, and then it relaxes down to the bottom of the S1 vibrational manifold. And that's an energy loss mechanism with the environment. No time for that to happen here. Things have very fast lifetimes, so up and down, up and down. So in this scenario B over here, we have a different excitation wavelength, and we get a different emission wavelength for the signature of the vibrational change. That's different from fluorescence. Fluorescence, if I excite at a slightly different wavelength, I will get essentially the same fluorescence spectrum. All that will happen will be that after I excite the molecule up, it has a little more energy that it gets rid of to its environment, and it lands in the same bottom of the well here. It has forgotten exactly what wavelength excited it. In this case, for Raman spectroscopy, the output photon in red, if you will, has an imprint or remembers the wavelength of the incident photon that excited it. So that tunability is an important thing. You have tunable excitation. You can use whatever wavelength you want within some bounds, but conceptually here, you're free to use different excitation wavelengths for whatever's more convenient for you, and you will get information about Raman scattering that's the same. So let's compare what fluorescence spectroscopy and Raman spectroscopy are ultimately reported as. In this experiment that we're seeing over here, if I think about it like a fluorescence experiment and I plot the observable lambda out, the wavelength of the outgoing photon, in these two experiments, A and B, if the experiment in A gives me a Raman peak that looks something like this here, and I'd call that the A peak, then in the B experiment, I have a more energetic incident photon, I'll have a more energetic output photon, so the peak in the B experiment might be over here at a shorter wavelength. Again, what I want to emphasize is that the spectrum shifts with excitation wavelength for Raman. The spectrum does not shift with excitation wavelength very much for fluorescence. So I'll emphasize that here by saying that fluorescence gives off the same spectrum as a function of lambda out, regardless of what exact wavelength you use to excite the fluorescence. A lambda out spectrum will look almost identical if you're looking at photons that were emitted fluorescently. But for Raman scattering, it's a different deal. We have approximately the same spectrum as a function of this energy shift parameter, delta nu tilde. And what I mean by that is that if you take this data and you replot it, not as a function of lambda out, but as a function of 1 over lambda of the laser minus 1 over lambda of the output photon, you would then get the A peak would show up like that, and the B peak would look exactly the same. You'd have A and B there. So you can, as I said, choose whichever wavelength you want to excite your spectrum at, and if you calculate this quantity here, you will get the same spectrum. And that's convenient. It allows you to use data that was acquired with excitation wavelengths other than the one that your laser happens to have. The last thing I want to say in this tutorial is to get into the conceptual idea of why are these new frequencies being created when a photon strikes a molecule. It kind of makes sense on the energy level, but it's nice to have some concept of what's going on. And here's what I would say about that. Suppose you start off with your molecule again, your little 2-atom molecule, and it's going to have some electron charge distribution. I'll just write this as some sort of notional cloud surrounding this. And if I come in now with my laser and I hit this molecule with a laser beam, I can think of some electric field coming in. Maybe I would write that as E0 e to the minus I omega t, so I have some cosine time dependence. And what I'm going to induce in these electrons, say, if I apply an oscillating electric field to the electrons, if you've studied the way dipole radiation is generated, you have electron oscillation that's going to occur, that's going to be shaking much, much greater amplitude than the nuclear charge. The protons are going to be shaking. So we have this electron oscillation that generates dipole radiation. And if the molecule weren't vibrating at all, if the atoms were staying in their place and not changing their separation from each other, we'd say there's no vibrational motion. And we would say that there's an induced dipole moment. The polarization, the separation of the positive charge center from the negative charge center, and we would refer as that we have an induced dipole. In this case, we give that the variable p, so the dipole moment as a function of time. What it would be equal to is some coefficient alpha, called the polarizability, and then the electric field, and I'll write that now in terms of real numbers, cosine of omega t. And what this is asserting is that if you apply a cosine of omega t electric field to something that's not changing its shape at all, you're just shaking the electrons around, you are going to radiate light. This dipole, which is going to do the radiating like an antenna, is only going to be oscillating at the frequency at which it's being driven. You can't get Raman scattering in that situation. That would be the case where the photon comes in at En and scatters off and leaves at the same frequency. So that's what we would call elastic scattering. Raman is inelastic scattering. So how do we get these new frequencies generated? Well, that's the function of the vibration of the molecule. So if we have vibrational motion, so if we are with vibrational motion, now imagine that as the molecules, 2 atoms, 2 nuclei get pulled farther apart, maybe that electron cloud becomes easier to shake, or maybe it becomes harder to shake. Whether either of those two cases, this alpha is no longer constant in time. As the 2 atoms vibrate and change their relative separation, the polarizability alpha also changes. So we're now going to end up in a situation where the dipole moment that's being induced as a function of time looks something like this. You have an alpha naught, which is just a constant like we have up here, and then we have a coefficient alpha 1, which does have some time dependence. We pick up a cosine of capital omega t. Remember, capital omega t, capital omega is the frequency of oscillation, not of the light, but of the vibration. And this is saying we now have some time-dependent polarizability of this molecule. And then I'll keep the rest of the terms on here, cosine of omega t, and at the end, the E naught. So once you buy into a formula like this that says that the polarizability of the electron cloud depends upon where the molecule is in its vibrational period, you can now put a bracket around these two terms, and I'll just call your attention to that you'll now pick up a cosine of capital omega t times a cosine of little omega t. That produces new frequencies. And I'm not going to go into the trig identity of it, but it happens to be that if you multiply cosine of A times cosine of B, you get cosine of A minus B and cosine of A plus B. And so in that case, we get one frequency, omega minus capital omega, and we call that Stokes Raman scattering. We use that same term in fluorescence. We say the light is red-shifted or Stokes-shifted. This is a lower frequency of photon, and therefore it's red-shifted from the laser. And you also predict that you'll get omega plus capital omega, and that's called anti-Stokes. It's the opposite of Stokes shifting. It's a blue-shifted photon. That does exist. We will talk in class about how relatively likely it is to have a Stokes versus an anti-Stokes peak. But that's the basic conceptual story of why a vibrating molecule will, when driven by a single pure frequency of light, will induce radiation in an antenna-like way, where the antenna is radiating not simply at frequency of the laser, but at new frequencies. That is the conceptual idea of the Raman scattering effect.